Hi everyone, I am Bhumika from BSc Honors First Year Chemistry. In this video, I am going to read Thermodynamics. Chemical energy stored by molecules can be released as heat during chemical reaction. When a fuel like methane, cooking gas, or coal burns in air, the chemical energy may also be used to do mechanical work when the fuel burns in an engine or to provide electrical energy through a galvanic cell like dry cell. Thus, various forms of energy are interrelated and under certain conditions they may be transformed from one form to another. The study of these energy transformation forms the subject matter of thermodynamics. The law of thermodynamics deal with the energy changes of macroscopic system involving a large number of molecules rather than the microscopic system containing a few molecules. Thermodynamics is not concerned about how and at what rate of these energy transformations are carried out but is based on initial and final states of a system undergoing the change. Law of thermodynamics apply once when a system is in equilibrium or moves fast from one equilibrium state to another equilibrium state. Microscopic properties like pressure and temperature do not change with the time for a system in an equilibrium state. In this unit, we have to answer some of the important questions of the thermodynamics like how do we determine the energy changes involved in the chemical reaction process? Will it occur or not? What drives a chemical reaction or process? To what extent the chemical reaction proceed? Thermodynamic terms. These are interested in chemical reaction and the energy changes accompanying them. For this, we need to know certain thermodynamic terms that are the system and the surrounding. A system in thermodynamics refers to that part of the universe in which observations are made and remaining universe constitute the surrounding. The surrounding includes everything other than the system. System and the surrounding together constitute the universe. The universe is equal to the system plus the surroundings. However, the entire universe other than the system is not affected by the changes taking place in the system. Therefore, for the practical purposes, the surroundings are that portion of the remaining universe which can be interact with the system. Usually, the region of space in the neighborhood of the system constitutes in surrounding. For example, if we are studying the reaction between two substances A and B kept in a beaker, the beaker containing the reaction mixture is the system and the room where the beaker is kept in the surrounding. The system from its surrounding is called boundary. This is designed to allow us to control and keep track of all movements of matter and energy in and out of the system. Types of system. First, open system. In an open system, there is an exchange of energy and matter between substance and system. This principle of the reactants in an open beaker is an example of open system. Here, the boundary is an imaginary surface enclosing the beaker and reactants. Closed system. In a closed system, there is no exchange of matter, but exchange of energy is possible between system and the surrounding. The presence of reactants in a closed vessel made of conducting material, example copper or steel, is an example of closed system. Isolated system. In an isolated system, there is no exchange of energy or matter between the system and the surrounding. The presence of reactant in the thermoflask or any other closed insulated vessel is an example of isolated system. The system state of the state of the system. The system must be described in order to make any useful calculation by specifying quantitatively each of the properties such as its pressure, volume, and temperature, as well as the composition of the system. We need to describe the system by specifying it and before after the change. You would recall from the physics course that the state of the system in mechanics is completely specified at a given instant of time by the position and velocity of each mass point of the system. In thermodynamics, a different and much simpler concept of the state of the system is introduced. It doesn't need detailed knowledge of the motion of each particle because we deal with an average measurable properties of the system. We specify the state of the system by function or state variables. The state of the thermodynamic system is described by its measurable and microscopic properties. We can describe the state of the gas by quoting its pressure, volume, and temperature. amount variables like PVT called state variables or state functions because their value depends only on the state of the system and not on how it is reached. In order to completely define the state of the system, it is not necessary to define all the properties of the system as only a certain number of properties can be verified independently. The system depends on the nature of the system. Once their minimum number of macroscopic properties are fixed, others automatically have definite values. The state of the surroundings can never be completely specified. Fortunately, it is not necessary to do so. The internal energy is a state function. When we talk about our chemical system losing or gaining energy, we need to introduce a quantity which represents the total energy of the system. It may be chemical, electrical, mechanical, or any type of energy you may think. The sum of all these energies is the energy of the system. In thermodynamics, we call it the internal energy E of the system, which may change when heat passes into or out of the system, work is done on or by the matter enters or leaves the system. These systems are classified according as you already studied in the section 5.1.2. Work. Let us examine a change in the internal energy by doing work. We can take the system containing some quantity of water in the thermal flask or in an insulated beaker. This would not allow change of heat between the system and the surrounding, though its boundary, and we call that the type of the system is adiabatic. The manner in which the state of the system may be changed will be called adiabatic process. Adiabatic process is a process in which there is no transfer of heat between the system and the surrounding. Here, the wall separating the system and the surrounding is called adiabatic wall. Let us bring the change in the internal energy of the system by doing the some work called. Let us call the initial state of the system as A and its temperature as TA. Let the internal energy of the system in the state A is UA. We can change the state of the system in two different ways. One way, we do some mechanical work, say 1 kilojoule, by rotating a set of small pedals by thereby churning water. Let the new state of the B state and its temperature as TB. It is found then TB is greater than TA and the change in the temperature, which is delta T is equal to TB minus TA. Let the internal energy of the system in state B be UB and the change of the internal energy delta U is equal to UB minus UA. Second way, we now do an equal amount of electrical work with the help of an immersion rod and note down the temperature change. We found that the temperature change in temperature in some is earlier case, say TB minus TA. In fact, the experiments in the above manner were done by J.P. Joule between 1840 to 1850, and he was able to show that given amount of work done on the system, no matter how it is done, produce the same change of the state as measured by the change in the temperature of the system. So, it seems appropriate to define a quantity, the internal energy U, whose value is characteristics of the state of the system, whereby the adiabatic work required to bring about a change of the state is equal to the difference between the value of U in one state and in another state. By the convention of IUPAC in the chemical thermodynamics, the positive sign expresses that the WAD is positive, then the work done on the system and the internal energy of the system increases. Similarly, if the work is done by the system, WAD will be negative because internal energy of the system can decreases. By the convention of IUPAC in the chemical thermodynamics, the Q is positive when heat is transferred from the surrounding to the system and the internal energy of the system increases, and Q is negative when heat is transferred from the system to the surrounding, resulted in the decrease of internal energy of the system. Applications. Many chemical reaction involves the generation of gases capable of doing mechanical work or the generation of heat. It is important for us to quantify these changes and relate them to the changes in the internal energy. Let us see how. First, work. First of all, let us consider the nature of the work of the system can do. We will consider only mechanical work, that is pressure, volume, and work. For understanding pressure volume work, let us consider a cylinder which is contains to 1 mole of an ideal gas fitted with a frictionless piston. Total volume of the gas is Vi and the pressure of the gas inside is P. If external pressure is P external, which is greater than the P, piston is moved inward till the pressure. So this is the diagram and it is a piston. Inside becomes equal to Pax. Let us change to achieve a single step and the final volume by Vf. During this compression, suppose piston move a distance L in the cross-sectional area of piston A. Then the volume change is equal to L into A is equal to delta V is equal to Vf minus Vi. We also know that pressure is equal to force upon area. Therefore, pressure on the piston is equal to Px into A. If W is the work done on the system by the movement of the piston, then W is equal to force into distance, which is Pex into A into L. So the total is equal to minus Px bracket Vf minus Vi. The negative sign of the expression is required to obtain conventional sign for W, which will be positive. It indicates that in the case of compression, work is done on the system where Vf minus Vi will be negative and the negative multiplied by the negative will be positive. Hence, the sign obtained for the work will be positive. If the pressure is not constant but changes during the process such that it always infinite similarly greater than the pressure of the gas, then at each state of compression the volume decreases by an infinitesimal amount dV. In such case, we can calculate the work done on the gas by the relation. Here, Px at each state is equal to the Pin plus dP. In case of compression, in an expansion process under similar conditions, the external pressure is always less than the pressure of the system. That is, Pex is equal to Pin minus dP. In general case, we can write Pex is equal to Pin plus minus dP. Such processes are called reversible processes. A process or change is said to be reversible if the change is brought only out in such a way that the process could be at any moment be reversed and by infinitesimal change. A reversible process proceeds infinitely slowly by a series of equilibrium states such that system and the surrounding are always in near equilibrium with each other. Free expansion. Expansion of gas in the vacuum is called free expansion. No work is done during the free expansion of the ideal gas, whether the process is reversible or irreversible. Now we can write the equation 5.1 in the number of the V's depending on the type of the processes. Enthalpy H, a useful new state function. We know that the heat absorbed at constant volume is equal to the change of the internal energy. But most of the chemical reactions are carried out not by the constant volume but in the flask or the test tube under constant atmospheric pressure. We need to define another state function which may be suitable under these conditions. We may write in equation as delta U is equal to Qp minus P delta V at constant pressures, where Qp is heat absorbed by the system and minus P delta V represent expansion work done by the system. Let us represent the initial state subscript and the final state by 2. We can rewrite the above equation U2 minus U1 is equal to Qp minus P bracket V2 minus V1. On rearranging, we get Qp is equal to U2 minus P U2 plus PV2 minus U1 plus PV1. Now we can define another thermodynamic function, the energy, the enthalpy H. Greek word enthalpion to warmth and heat content. H is equal to U plus PV. So equation becomes QV is equal to H minus H2 minus H1 is equal to delta H. Extensive and intensive property. In thermodynamics, a distinction is made between extensive properties and intensive properties. An extensive property is a property whose value depends on the quantity or size of the matter present in the system. For example, mass, volume, internal energy, enthalpy, heat capacity are extensive properties. Those properties which do not depend on the quantity or the size of the present are known as intensive property. For example, temperature, density, pressure, etc. are intensive properties. A molar properties Xm is equal to the extensive property X of the system. For 1 mole of the substance, if N is equal to the amount of matter, is independent of the amount of matter. Other examples like molar volume and molar heat capacity. Let us understand the distinction between the extensive and the intensive property by considering a gas enclosed in a container of volume V and temperature T. Heat capacity. In the subsection, let us see how to measure the heat transfer from a system. This heat appears in the rise in the temperature of the system in case that the heat absorbed of the system. The increase of temperature is proportional to the heat transferred. Q is equal to coefficient into delta T. The magnitude of the coefficient depends on the size, composition, and nature of the system. We can also write it as Q is equal to C delta T. The coefficient C is called the heat capacity. Thus, we can measure the heat supplied by monitoring the temperature rise provided we know the heat capacity. When C is large, the given amount of heat result in the small temperature rise. Water as heat, large heat capacity, a lot of energy is needed to raise the temperature. C is directly proportional to the amount of substance. The molar heat capacity of a substance is the heat capacity for 1 mole of the substance and is quantity of the heat needed to be raised the temperature of 1 mole of by 1 degree Celsius. Specific heat, also called specific heat capacity, is the quantity of heat required to raise the temperature of 1 unit mass of a substance by 1 degree Celsius. For finding out the heat required to raise the temperature of sample, we multiply the specific heat of the substance C by the mass m and the temperature change T delta T is equal to Q is equal to C into m into delta T, which is equal to C delta T. Measurement of delta U and delta H calorimetry. We can measure energy changes associated with chemical or physical processes by an experimental technique called calorimetry. In calorimetry, the process is carried out in the vessel called calorimeter, which is immersed in a known volume of a liquid. Knowing the heat capacity of the liquid in which calorimeter is immersed and the heat capacity of the calorimeter, it is possible to determine the heat involved in the process by measuring temperature changes. Measurements are made under two different conditions. First, at constant volume. Second, at constant pressure. Delta U measurement for chemical reaction. Heat absorbed at the constant volume is measured in a boom calorimeter. Here, a steel vessel is immersed in the bathtub, in the water bath, and the whole device is called calorimeter. The steel vessel is immersed in the water bath to ensure that no heat in the surrounding. A combustible substance is burnt in a pure dioxygen supplied in the steel boom. Heat involved during the reaction is transferred to the water around the bomb and its temperature is monitored. Since the bomb calorimeter is sealed, its volume does not change. The energy changes associated with reactions are measured at the constant volume. Under these conditions, no work is done as the reaction is carried out at constant volume in the bomb calorimeter. For reactions involving gases, there is no work done as delta V is equal to 0. The temperature change of the calorimeter produced by completed reaction is then converted to QV. By using the non-heat capacity of the calorimeter, the heat help of the equation 5.11. Delta H measurements of the heat change at constant pressure can be done in a calorimeter. We know that delta H is equal to Qp and therefore heat absorbed or evolved Qp at constant pressure is also called the heat of reaction of enthalpy. In exothermic reaction, heat is involved and the system loses heat to the surrounding. Therefore, Qp will be negative and delta Rh will also be negative. Similarly, in an endothermic reaction, heat is absorbed, Qp is positive and delta Rh will be positive. Enthalpy change delta Rh of the reaction enthalpy. In a chemical reaction, reactants are converted into products as represented by reactants into products. The enthalpy change accompanying a reaction is called reaction enthalpy. The enthalpy change of the chemical reaction is given by symbol delta Rh. Here, the sigma is used for summation of AI and BI are the stoichiometric coefficients of the products and the reactants respectively in the balanced chemical equation. For example, this enthalpy change is a very useful quantity. Knowledge of this quantity is required when one need to plan the heating or cooling required to maintain an industrial chemical reaction. Example, at a constant temperature, it is also required to calculate the temperature dependence of equilibrium constant. Standard enthalpy of reactions. Enthalpy of reaction depends on the conditions under which a reaction is carried out. It is therefore necessary that we must specify some standard conditions. The standard enthalpy of the reaction is the enthalpy change for a reaction when all our participating substances are in their standard states. The standard state of a substance at a specified temperature is its pure form of 1 bar. For example, the standard state of liquid at 298 Kelvin is a pure liquid ethanol at 1 bar. Standard temperature, standard state of solid iron at 500 Kelvin is a pure iron 1 bar. Usually, data are taken as 298 Kelvin. Standard conditions are denoted by adding the superscript to the symbol delta H. Enthalpy changes during phase transformation. Phase transformation also involve energy changes as, for example, require heats for melting. Normally, this melting takes place at constant pressure and during phase change, temperature remains constant. Here, delta fusion H negative is the enthalpy of fusion in the standard state. If water freezes, then process is reversed and equal amount of heat is given off to the surroundings. The enthalpy change of that accommodates melting of 1 mole of solid substance in the standard state is known as standard enthalpy of fusion or molar enthalpy of fusion. Melting of solid is endothermic, so all enthalpies of fusions are positive. Water requires heat of vaporization at constant temperature of its boiling point, TB, and at constant pressure. Amount of heat required to vaporize 1 of mole of the liquid at constant temperature and standard pressure is called standard enthalpy of vaporization or molar enthalpy of vaporization. Sublimation is direct conversion of solid into its vapor. Solid CO2 or dry ice sublimates at 195 Kelvin. Naphthalene sublimates slowly. For this, standard enthalpy of sublimation is the change in the enthalpy when 1 mole of solid substance sublimates at constant temperature and under standard pressure. The magnitude of the enthalpy change depends on the strength of the intermolecular interaction in the substance undergoing the phase transformations. For example, the strong hydrogen bonds between water molecules hold them tightly in liquid phase for an organic liquid such as acetone. The intermolecular dipole-dipole interaction are significantly weaker. Thus, it requires less heat to vaporize 1 mole of acetone than it does to vaporize 1 mole of water. Table 5.1 gives value of standard enthalpy changes of fusion and vaporization for substances. Standard enthalpy of formation. The standard enthalpy change for the formation of 1 mole of compound from its elements in its most stable states of aggregation is also called standard mole enthalpy of formation. Its symbol is delta F H negative, where the subscript F indicates the 1 mole of the compound in the question has been in its standard state for its element in the most stable of their aggregation. The reference state of the elements is its most stable state of aggregation at 25 degrees Celsius and 1 bar pressure. For example, the reference state of dihydrogen is H2 and those dioxygen, carbon, and sulfur are O2 gas, C graphite, and C and S rhombic respectively. Some reactions with standard molar enthalpy of formation are as follows. It is important to understand that a standard molar enthalpy of formation is just a special case where 1 mole of compound is formed from its constituent elements is above 3 equations where 1 mole of each water, methane, and ethanol is formed. In contrast, the enthalpy of change of the exothermic reaction. It is not an enthalpy of formation of calcium carbonate since calcium carbonate has been formed from other compounds and not from its constituents elements. Also, for the reaction given below, enthalpy change is not standard enthalpy of formation. Here, 2 mole instead of 1 mole of the product is formed from the elements. Therefore, by dividing all the coefficients, the balance equation by 2 expression for enthalpy of formation of HBr is written. Standard enthalpies of the formation of common substances. By convention, standard enthalpy for formation of an element in reference state, the most table of aggregation is taken as zero. Suppose you are the chemical engineer and you want to know how much heat is required to decompose calcium carbonate to lime and the carbon dioxide with all substances. Their standard state is CaCO3, which is in solid form, gives CaO and CO2, which is in solid and gas form, respectively. Here we can use of standard enthalpy of formation and calculate the enthalpy for the reaction. The following general equation can be used by the enthalpy change calculation where A and B represent the coefficient of the products and the reactants in balance equation. Let us apply the above equation for decomposition of calcium carbonate. Here coefficients A and B are 1 for each other. Thus, decomposition of CaCO3 is an endothermic process and you have to heat it for getting the desired products. Thermochemical equations are balanced chemical equation together. The value of delta RH is a thermochemical equation. We specify the physical state of the substance in the equation. The above equation describes the combustion of the liquid ethanol at the constant temperature and pressure. The negative sign of the enthalpy change indicates that there is an exothermic reaction. It would be necessary to remember the following convention regarding thermochemical equation. The coefficient is balanced thermochemical equation refers to the number of moles of the reactants of the products involved in the reaction. The numeric value of delta RH refers to the number of moles of the substances specified by the equation. Standard enthalpy change delta RH will have units of kilojoule per mole. To illustrate the concept, let us consider the heat of the calculation of the reaction for the following reaction is this. From the table of the enthalpy of formation, we find that the delta FH negative is equal to 0 as per convention. Note the coefficients used in these calculations are pure numbers which are equal to the respective stoichiometric coefficient. The unit of RH negative is kilojoule per mole, which means the mole of the reaction once we balance the chemical equation in the particular way as above. This defines the mole of reaction. It has a balanced equation differently. Hess law of constant heat summation. We know that the enthalpy is a state function, therefore, change in enthalpy is independent of the path between the initial state and the final state. In other words, the enthalpy change for a reaction is same whether it occurs in one step or in series of steps. This may be stated as follows in the form of Hess law. It is a reaction takes place in a several state, that is standard reaction enthalpy is the sum of the standard enthalpies of the intermediate reaction into which the overall reaction may be divided as the same temperature. Let us understand the importance of this law with the help of an example. Consider the enthalpy for the change of the reaction. Although carbon monoxide is the major product, some carbon dioxide gas will always produced in this reaction. Therefore, we cannot measure enthalpy change for the above reaction directly. However, it can be found from some other reactions involving specific related species. It is possible to calculate the enthalpy change for the above reaction. We can combine the above two reactions in such a way so that it offers the desired reaction to get 1 mole of carbon monoxide on the right. We reverse the equation. In this reaction is absorbed instead of being released. So we change the sign of RH negative value. In general, if enthalpy of overall reaction is A to B, along one route has delta RH in one species, delta RH1, delta RH2, and delta RH3 representing the enthalpies of the reactions leading to the same product B along the another route. Since the combustion of glucose gives out 2802.0 kilojoule per mole of the heat for the overload reaction, equation is glucose plus 6CO2 gives to 6CO2 and 6H2O. Our body also generates energy from food by same overall process as a combustion, although the final products are also produced in series of complex biochemical reaction involving enzymes.